Hörmətli tədbir iştirakçıları, hər birinizin günortası xeyir olsun. Mən sizi salamlayıram. Biz hamımız bugün səhər Cəlal Əliyevin 90 illik yubileyinə həsr olmuş tədbirdə iştirak elədik. Böyük arzularla, böyük xoş ürək açıqlığı ilə ayrıldıq tədbirdə və bugün bizim tədbirimizin indi ikinci hissəsi başlayacaq və yubiley tədbirdə eşitdiniz. Beynəlxalq Fotosintez Cəmiyyəti Cəlal Əliyev adına mükafat təsis etmişdir və bu mükafatın ilk laureatı, mükafata layiq görülən Profesör Şendir. Mən həm Fotosintez Cəmiyyətinin katibi Profesör Elton Rayı, həm də Profesör Şeni salamlayıram. Bakıda görməkdən çox xoşuq və onları yenidən Bakıya görmək istəyərdik. Hər birinə uzaq yolu gəldiyinə görə, yəni Profesör Elton Ray Yeni Zelandiyadan bizim ölkəmizə gəlibdi, Bakıya gəlibdi, uzaq bir yol keçibdi və Profesör Şen, yəni ki bugün havanın soyuq vaxtında Bakıya gəlmək o da bir ağır, çətin yoludur. Yəni hər ikisinə mən dərin minnətdarlığımı bildirirəm. Bizim bugünkü tədbirimizdə eyni zamanda Cəlal müəlliminin tələbələri, iki tələbəsi iştirak edir, xaricdən olan tələbələri. Mən Süleyman müəllimi də salamlayıram burada, xoş gəlmişsən deyirəm. Süleyman müəllim öz evinə gəlibdi, öz laboratoriyasına gəlibdi, işlərin yanına və çox şadıq ki, yenidən siz buradasınız, bizimləsiz. Mən İsmail müəllimi də salamlayıram. İsmail müəllim, Cəlal müəllimi tələbəsi kimi bu yubiley tədbirlərində iştirak etmək üçün Cənubi Koreyadan Pusan Milli Universitetinin Molekulyar Biologiya departamentindən gəlibdi, uzaq yol gedibdi və İsmail müəllim lap axırıncı dəqiqələrdə, yəni ki, bilet ala bildi, gəlib çıxa bildi. Biz sizi də salamlayırıq, minnətdarlığımızı bildiririk və Əhməd bəy Fransadan gəlib, Parisdən və Əhməd bəy də mən deyərdim ki, artıq Azərbaycanlıdır və yəni ki, mən Şimali Azərbaycanlısı deyərdim. Çünki Əhməd bəy ildə, hər il heç olmasa 2 dəfə Bakıya gəlməzsə, sakit olmur. İnşallah bu il bir dəfə gəlibdir. Fikirləşirəm ki, gələn il bunu əvəz eləyərik, kompensasiya edərik və o say tamam olar. Əhməd bəy, xoş gəlmişsiniz, salamlayıram. Mən bütün qonaqlarımıza minnətdarlığımı bildirirəm. Yəni ki, Cəlal müəllimə olan diqqətlərinə görə, burada iştirak edilərinə görə, eyni zamanda bizim burada başqa institutlardan olan həmkarlarımız əyləşibdir, universitetdən olan həmkarlarımız əyləşibdir. Hər birinə minnətdarlığımı bildirirəm, gəlib bu tədbirdə iştirak etdiyinə görə və eyni zamanda bizim burada gənclərimiz əyləşibdir. Və bilirsiniz ki, Cəlal müəllimin yubiley tədbirinə biz Azərbaycan Milli Elmlər Akademiyasında ilkin olaraq gənclərin konfransı ilə başladıq və çox yüksək səviyyədə konfrans keçdi. Gənclərimiz öz biliklərini nümayiş etdirdi və bu da bir simbolik mənadır. Çünki Cəlal müəllim həmişə gəncliyə diqqət eləmişdi, gənc kadrların yetişməsinə diqqət eləmişdi və bugün artıq bizim yubiley tədbirimizin əsas anıdır və qeyd etdiyim kimi Beynəlxalq Fotosintez Cəmiyyətinə, onun rəhbərinə, bugün burada iştirak edən Profesör Elton Raya biz dərin minnətdarlığımızı bildiririk ki, Cəlal müəllimə diqqət elədilər, belə bir mükafatı təsis etdilər və Cəlal Əliyevin şərəfinə 9-cu Beynəlxalq davamlı inkişaf naminə fotosintez və hidrogen enerjisi tədqiqatları konfransının keçirilməsi haqqında qərar qəbul etdilər. Qeyd etdiyim kimi, Cəlal Əliyev adına təsis olan mükafatın ilk nominantı Profesör Şendir. Mən onun haqqında bayaq imkan olmadı, yəni ki, çıxışlar çoxudur. Biz daha dəqiq məlumat verə bilmədik. İndi icazə verərdiniz, mən o əsas məlumatları çatdırım və sonra sözü biz Profesör Şenə, onun prezentasiyasında qulaq asmaq üçün verək. Profesör Şen, demək, 1961-ci ilin oktyabr ayında Çin Xalq Respublikasında anadan olubdu. O hal-hazırda Fənlər Arası Elmi Tədqiqat İnstitutunun profesoru və dekan müavinidir, Yaponiyanın Akayama Universitetində. Profesör Şen, Çinin Gəncə Kənd Təsərrüfatı İnstitutunu 1982-ci ildə bitirmiş, Yaponiyanın Tokyo Kənd Təsərrüfatı və Texnologiya Universitetinin magistraturasına daxil olmuş və 1986-cı ildə magistr dərəcəsi almışdır. Sonra o Tokyo Universitetində doktoranturaya daxil olmuş və 1990-cı ildə fəlsəfə doktoruna layiq görülmüşdür. 1990-97-ci illərdə alim Yaponiyanın məşhur Riken İnstitutunda Günəş Tədqiqatları qrupunda tədqiqatçı alim kimi işləmişdir. 1997-2003-cü illərdə həmin institutda böyük ilmi işçi kimi fəaliyyət göstərmişdir. 2003-cü ildən bu günə kimi Yaponiyanın Akayama Universitetinin professorudur. O, hal-hazırda Fənlərarası Elm Tədqiqat İnstitutunun professoru və dekan müavinidir. Yəni, bizim qulağımızın nə qədər nüfusu olduğunu görürsünüz. Professor Şinin əsas elmi tədqiqatları fotosintetik sistemlərin struktur və funksiyasını əhatə edir. O, 2011-ci ildə ilk dəfə olaraq fotosistem 2-nin quruluşunu 1.9 angstrom dəqiqliyi ilə müəyyən edə bilmişdir və bu nəticələr Nature jurnalında çap olunmuşdur və bu nailiyyət Science jurnalında 2011-ci ilin kəşfi adını almışdır. O, öz qrupu ilə birlikdə fotosistem 2-nin radiasiyadan zədələnməyən quruluşunu, bu məqalə 2015-ci ildə Nature jurnalında çap olunubdur. Fotosistem 2-nin aralıq quruluşunu yenə də Nature'nin 2017-ci ilində çap olunubdur. Ali bitkilərdə fotosistem 1 ışıq toplayan kompleks bir quruluşunu bu məqalə Science-da 2015-ci ildə çap olunubdur. Fotosintetik bakteriyada deməli bir reaksiya mərkəzinin quruluşunu, bu isə son olaraq Nature jurnalında 2018-ci ildə dərc olunmuşdur. Onun bir çox mükafatlara layiq görülmüşdür. O cümlədən Professor Shin Yaponiyada deməli nüfuzlu Aşahi mükafatı 2013-cü ildə və Yaponiyanın baş nazirinin yaşıl elm üzrə mükafatını 2017-ci ildə almışdır. Biz qonağımız haqqında əsas məlumatları verdik və bizim qonağımızın, yəni ki, mən fikirləşirəm ki, Cəlal Əliyev necə bir nüfuzlu alimidir və onun adına olan mükafatı alan alim də məhz Professor Shen kimi bir alim olmalıdır. Biz buna çox sevinirik və qeyd etmək istəyirəm ki, Professor Shen'i biz artıq Bakıda bir dəfə də görmüşük, yəni ki, gəlib, iştirak edib, çıxış edibdir bizim konfransımızda. Mən yenidən öz adımdan, bizim institutların adından, yəni həm Molekulyar Biologiya və Biotexnologiyalar İnstitutunun, həm Əkinçilik İnstitutunun kollektivi adından bütün qonaqlarımıza, o cümlədən Professor Şinə dəqiq minnətdarlığımı bildirirəm və mühazirəni prezentasiyanı təqdim etmək üçün onu buna dəvət edirəm. Sağ olun.
Thank you, Professor Ilata, for your kind introduction. And I'm very honored and pleased to receive the first Professor Cəlal Əliyev's award from today. And this is the second time I visited Baku, and I met Professor Əliyev in 2011 when I first time visited Baku, and I know his work is very famous in the field of photosynthesis. So I'm very happy to receive the first award in honor of Professor Cəlal Əliyev. So I would like to introduce our work that has been selected by the International Society for Photosynthesis Research, and the award in honor of Professor Cəlal Əliyevin. So my talk today is the structural biological studies of photosynthetic membrane protein complexes. So as all of you know, that photosynthesis is the process by which plants and various photosynthetic organisms utilizes sunlight, energy from the sunlight, to convert from water and carbon dioxide, focused on the carbon dioxide fixation, which makes sugars and provides food for us, and also provides the stocks for fossil fuels, which we use today. And this process sustains almost all life forms on the earth by providing food and energy and then oxygen. So we are interested in the mechanism, not only me and many of scientists are interested in the mechanism of these reactions. And as you can see, this in the chemical form, it can be written by this reaction from water and carbon dioxide. It's converted into carbohydrates, and oxygen is evolved. And of course, this reaction requires energy, which is provided by sunlight. and produces a lot of oxygen every year, and at the same time fix carbon dioxide into sugars and organic compounds. We are particularly interested in the first half of the reaction, which utilizes light energy to split water to evolve oxygen. And by this reaction, the energy in the form of this light is converted into the form of chemical energy. Then it can be utilized to fix carbon dioxide. And during this process, water is oxygen is evolved. And this reaction, the light reactions, take place in the membranes, which is called the cell called the membrane. And there are several kinds of membrane protein complexes involved. The first one is called the photosystem 2, PS2, which utilizes light energy to convert, to split water, then to evolve oxygen. And then at the same time, protons are evolved and electrons are removed from the water molecules. And the protons are accumulated in the one side of the membrane, which is now utilized by ATP synthase to synthesize ATP. An electron evolved is transferred through another protein complex, which is cytochrome B6F complex, and then to another protein complex, which is photosystem 1 complex. And finally, it is transferred to NADPH, reduce NADPH into NADP plus into NADPH. And these two compounds generated NADPH and ATP provides the energy and is reducing power to convert carbon dioxide into sugars. So the very first reaction catalyzed by photosystem 2 can be written here. From two water molecules, it is split into one molecule for oxygen and 4 protons and 4 electrons. And it is catalyzed by photosystem 2, utilizing the energy from the sun. We are interested in this reaction because through this reaction, the energy is converted into the energy of protons and electrons. And they are finally converted into ATP and NADPH. And also, one of the products is molecular oxygen. This is the source of oxygen in the atmosphere that we breathe and we utilize every day. Otherwise, if there's no this kind of reaction, there will be no oxygen in the atmosphere. Actually, if you consider the evolution of Earth's atmosphere, the composition of Earth's atmosphere, at the beginning of the birth of Earth, which is around 4.5 billion of years ago, there was no oxygen at all in the atmosphere, and it is occupied by carbon dioxide and some other kinds of reducing gases. And around 3 to 3.5 billion of years ago, the first photosynthetic oxygenic organism appeared. Here, then oxygen is released gradually, and it is accumulated gradually in the atmosphere, which actually took around 2 billion of years for the oxygen to accumulate to a level of current atmosphere. And because of this accumulation of oxygen, it transformed the atmosphere from a reducing one to an aerobic oxygenic one. And this enabled other types of organisms to evolve, which is the oxygenic life, using oxygen as during respiration. So nowadays we all utilize oxygen for respiration, and this is generated by this water splitting reaction catalyzed by photosystem 2. And when the oxygen level in the atmosphere accumulated reaches to the current level about 40 to 60 millions of years ago. The another important law of oxygen is to make ozone from oxygen, because ozone is produced from oxygen by illumination with ultraviolet light from the sun. And these two, oxygen and ozone concentrations, when they reach the current level of atmosphere, organisms were able to go to the land and began to use oxygen as in respiration. And this led to the evolution of a vast number of organisms in the land. And this period is called the explosion of biological evolution, the biological Big Bang of evolution, because of a large number of species appeared in this period of the time. One largely due to the accumulation of oxygen and ozone in the atmosphere. So another important reason we are interested in the mechanism of this reaction is that if we can make artificial catalyst to catalyze this reaction, then we may be able to obtain protons and electrons from the water and the sunlight. And these two products can be easily recombined to generate hydrogen fuels that can be supplied to industry and maybe also cars, to drive cars. So this is the field of artificial photosynthesis. And the most important bottleneck for this realization of this reaction is you need a catalyst. And so far, the most important and efficient catalyst in the nature is this protein complex, which is photosystem 2. So we are interested in the structure and the function of this protein complex and how this protein complex catalyzes this reaction. This reaction, water splitting reaction, proceeds through 4 steps because you need to remove 4 electrons from 2 water molecules, and the catalyst undergoes during each step undergoes some structure changes. Every time when 1 photon comes in, 1 electron is removed, and the catalyst goes to the most stable one is in the S1 state. And when 1 photon comes in, 1 electron is removed, and this catalyst goes to S2 state. And the second photon comes in, 1 electron is removed again, and proton is also removed. Then it goes to S3 state, and so on. Then finally, in this step, 1 molecule of oxygen is released, and the catalyst comes back to S0 and again to S1 state. So in order to solve the mechanism of this reaction, we needed to know the structure of the catalyst. So we started to solve the structure of PS2 by crystallizing this protein complex and using the X-ray crystallography to solve the structure. But this protein complex, I say it is a protein complex, consists of 20 protein subunits, different protein subunits, among which 17 are transmembrane protein subunits, and 3 are hydrophilic protein subunits. So it has a total molecular weight of 350 kilodalton, and it is a very big and complicated protein complex. So we are lucky to be able to make very good crystals of this PS2, which is shown here. And with this kind of crystals, we were able to solve the structure of PS2 at a resolution of 1.9 angstrom here. You can see it is PS2 forms a dimer. In the middle, it divides to monomers, and because it is a dimer, it consists of 40 different subunits with a total molecular weight of 700 kilodalton. And of course, because this is a very big protein complex, it carries out a number of reactions. When light comes in, there are several water pigments, chlorophyll molecules, who can absorb light energy and then results in a series of electron transfer reactions. So when we remove these protein backbones and just look at the reactions within this protein complex, you can see here, this is arrangement of the molecules which participate in the electron transfer, light absorption reactions. In the middle, you see there are 4 green molecules, which are chlorophyll molecules. And when one photon comes in, one of these 4 chlorophyll molecules absorbs one photon, then one electron is ejected. It is excited and ejected from one of these 4 chlorophyll pigments. And this electron is then transferred to nearby several molecules. The first one is a phyophytin. Actually, this is discovered by Professor Klimov, and I think he's one of the students of Professor Əliyevin. It's phyophytin. It's the first electron acceptor in PS2. And this electron then goes to 2 prostoquinones, which are called QA and QB, bound to protein subunits, which is one is D2 and one is D1 subunits. Then, because one electron is ejected from this chlorophyll molecule, one of the chlorophyll molecule becomes oxidized, and it becomes a plus cation and cation. And it wants to extract one electron from a nearby molecule. This is the one of the amino acid residue, tyrosine, here located here. And this tyrosine residue donates one electron to the chlorophyll, then it becomes oxidized, and also wants to extract one electron from nearby molecule. And this nearby molecule is a manganese 4 calcium cluster located here, very close to this tyrosine. And this manganese calcium cluster also wants to extract electron from nearby molecule, but there is no more molecules that can donate electron except the water molecules in its vicinity. So the manganese calcium cluster extracts electrons from water molecules. And when this reaction proceeds 4 times, then 4 electrons are removed from 2 water molecules, and 2 water molecules are suddenly split to produce 1 molecule of oxygen and 4 protons. So this is the whole reaction occurring in PS2 complex. And you can see that the catalyst that catalyzes water splitting directly is the manganese calcium cluster located here. So we are also interested in the structure of this manganese calcium cluster and how it functions to split water molecule. So we want to look at the structure of this manganese calcium cluster, and it is located here, which is in the surface of the membrane, in the side. Sorry, it cannot show me. Okay. Okay. When we took the structure, the manganese calcium cluster out from the protein complex and enlarge it, you can see here it is composed of 4 manganese ions and 1 calcium ion here. And they are connected by 5 oxygen atoms. And if we look at from this direction, it looks like a chair form, but this chair form is slightly distorted. So we call it the distorted chair form for the catalytic center for oxygen, for water splitting and oxygen evolution. And this kind of distorted form suggests that this catalyst is somewhat unstable. This is one of the most important features we can see from the structure, that because it is distorted, it is stable, and we think that it has some flexibility, which means that it is easily to undergo structure changes, can change its shape very easily. And this is exactly required for the catalyst. When the catalyst catalyzes the water splitting, I mentioned that there are 4 steps, and each step the catalyst will change its shape slightly. And because this kind of distortion, it's very easily to change its shape, which means that you need only very low energy to catalyze the water splitting reaction. And this structure we first reported it in 2011, and at that time the structure was solved by using X-rays from synchrotron X-ray radiation facility, which is a very strong X-rays and continuous X-rays. And using this kind of strong and continuous X-rays, there is a possibility that you will destroy the proteins or the metal ions. And in fact, when we reported the first time the structure, you can see these are the manganese ion distances here, 2.8 angstrom, 2.9 angstrom, and 3.0 angstroms. And these distances was suggested based on the theoretical calculations using our structure later, based on the quantum mechanical and molecular mechanical calculations. The distances were suggested to be slightly shorter from the calculations, in the range by 0.1 to 0.2 angstrom shorter from the theoretical calculations. And one of the reasons that was suggested is that in our experimental structure, the metal cluster may have suffered from radiation damage, causing some reduction of the manganese ions. If the manganese ions are reduced, their distance will become longer. And because we used continuous strong X-rays, there is a possibility for radiation damage to occur with the structure. And I mentioned that the structure is distorted. One of the major reasons in causing the distortion in the structure is that the distances between manganese and oxygen is not the same within this cluster. The typical oxygen manganese distances are in the range of 1.8 to 2.1 angstroms. And this is the same for typical manganese oxides. Even for inorganic manganese oxides, the distances between oxygen and manganese are in the range of 1.8 to 2.0 and something. But there is a very unique oxygen, the 5th oxygen here, O5. It has a distance to the nearby manganese ions of 2.5 and 2.6 angstroms. And these distances are extremely longer than the typical oxygen-manganese distances. And these differences in the distances is one of the major reasons causing the distortion of the structure. And also just suggests that this O5 is in a unique position, different from the other 4 oxygen atoms, from O1, O2, O3, and O4. But if the structure is suffered from radiation damage, then there is a possibility also for this O5 position may have been changed due to the radiation damage. So we have to solve the structure without radiation damage. And when we consider how the radiation damage caused by X-rays are occurring, when strong X-rays illuminate materials or crystals, strong X-rays will cause ionization of water molecules and producing reactive oxygen species. And these reactive oxygen species will attack proteins and metal ions and causing reduction of manganese ions. And then finally, the structure will be changed. And this process, the total process, occurs in the time range of picoseconds. That means 10 to the 12 miles power, picoseconds. So in order to remove the radiation damage, in principle, we need to collect the data in a time less than 1 picosecond. The time we used to collect the data with the strong X-rays, synchrotron radiation X-rays, is usually in the range of 0.5 to 1 seconds. So we have to use very short X-ray laser pulses, less than 1 picosecond. And this is can be provided by X-ray free electron laser. It's exactly what X-ray free electron laser can provide. This is the first facility in Japan. It's the world's second XFEO, X-ray free electron laser facility, and each X-ray from this XFEO facility, Sakura, has a time dilation of 10 femtoseconds. So if we can use this XFEO to collect data from crystal crystals and then solve the structure, we will be able to remove the radiation damage and to see the structure in its native state without radiation damage. So we used this kind of crystal crystals and the XFEO laser to collect the data and solve the structure again at a resolution of 1.95 angstrom in 2015. And we were able to determine the position of each atoms based on their electron density from the XFEO data. And then, okay, there's no distances. We determine the manganese distances. It's not shown here. The distances became 0.1 to 0.2 angstrom shorter between manganese ions, and which suggests that the structure is radiation damage free. So we look at the position of this O5 again. It is located here. It has a distance to the nearby manganese ions, 2.3 and 2.7, compared to the previous 2.5 and 2.6. It's a little bit changed, but compared with the typical oxygen manganese distance, it's still extremely longer, suggesting that this O5 still is in a unique position and it binds to the manganese ions very weakly. And suggests that because its binding is very weak, this oxygen may be cut out during the reaction cycle to provide one of the oxygen atoms for the OO bond formation for molecular oxygen. So this suggests that the area involving this O5 will be the reaction site for the O bond formation. Here, oxygen, molecular oxygen, may be produced involving the area here, involving this O5. And in very close position, there are two water molecules, W2 and W3, close to O5. So this area involving 3 oxygen atoms may be the reaction site for the O1 formation for oxygen production. But of course, there are 3 oxygen atoms in this area. We don't know which 2 of the 3 oxygen atoms will come closer to form an oxygen molecule. So we need to, because there are several possibilities. For example, there may be water molecule coming to this right side of O5 to form an O bond with O5, or coming to the left side of O5 to form an O bond. Or this water molecule may be a completely new water molecule. It is also possible that one of these 2 water molecules may come closer to O5 to make an O bond. And finally, there's also a possibility that these 2 water molecules may come closer to make an O bond to produce oxygen. This mechanism, all of these possibilities are based on the structure we solved in the S1 state, which is the dark stable state before reaction occurs. So in order to identify which mechanism actually works, we want to solve some of the intermediate structures to see how this catalyst undergoes structure changes by light illumination. And we first focused on S3 state, which is produced by 2 photons excitation. And you remove 2 electrons. Then S1 state will go to S3, because the S3 state is the last state before oxygen molecule is released. So we try to solve the structure of S3 state, again by using the XFEO, X-ray electron laser. And this is the experiment that we did. We provide small crystals from the upside to here. And we first illuminate with 1 light, laser light, visible laser light. Then after 10 milliseconds, we provide the second laser light. So it provides 2 photons. Then after 10 milliseconds again, we provide 1 X-ray electron laser to collect the data from here. And this is the data is from S3 state, because we provided the 2 visible lasers to excite the S1 state. I'm not sure it will work again. Okay, it's not working. Sorry. Yes. These are the crystals, very small crystals we used. And finally, we got electron density from the S3 state. And what we did is that we calculated the differences between the S1 state and S3 state. If the structure changes, we should be able to see the different electron density by subtracting the electron density from S1 by S3 minus S1. And if the structure remains the same, there will be no difference electron density. And this is the whole PS2 dimer. You can see in most of the area, there are no difference signal, but there are 3 areas. One is here, the second one is here, and the third one is here. These areas shows a difference electron density, which means that the structure has been changed due to the true light illumination. I will explain this structure changes. The first one, the first one is here. But before I explain the structure changes, I will explain you how it will look like. Before light illumination, if one atom is located in this position, A1 position, if this atom is moved to this position due to the light illumination, then when we do a subtraction of the electron density, we will see a pair of negative. Red one is negative, and this green one is positive electron density, which means that one atom has moved from this position to this position, towards this direction, because this is negative and electron density, and this is positive electron density, and we are calculating S3 minus S1 difference electron density. This is one case. The second case is that if there is one atom originally located here, and this atom disappeared after 2 illumination, laser illumination, then after subtraction, we should be able to see a negative electron density, which means that there is some atom originally located here, but it is disappeared from this position, from its original position, moved to somewhere else, or this atom is disordered, means that it's no more located in this position. The third case is that in the original position there is nothing here, but if one atom comes into this position due to laser illumination, then we should be able to see a positive electron density, like here. Green one is positive, and red one is negative electron density. So the structure changes. The first case, the first area is here. We saw a negative electron density, which means that some atom has moved somewhere else from this position. And in the original position, we see a water molecule, which is hydrogen bonded to this amino acid residue, which is YD, we call it tyrosine D. And after 2 flash illumination, this water molecule moved to this area, this position, and we saw a negative electron density. And this water molecule in S1 state is hydrogen bonded, but in S3 state, it's no more hydrogen bonded with the tyrosine residue. And this is caused by hydrogen proton release from this site, caused by 2 flash illumination in our crystal. The second area we saw the structural differences is around the QB area. This QB is the electron acceptor in the D1 subunit. We saw a pair of positive and negative electron density, which means that this QB has rotated from here to in this direction. And in corresponding to this rotation, the head of the QB is rotated in this direction slightly. This causes hydrogen bonding in the 2 sides to a shorter distance. And this is caused by the accept of 1 electron in some of the QB, prostoquinone, and some of the QB becomes QB minus. And because the head becomes QB minus, its hydrogen bond to the nearby hydrogen amino acid residues becomes stronger, and the distance becomes shorter. This is indication of QB minus, the presence of QB minus in our sample, because we used a very short time, 10 milliseconds, and some of the QB remains as QB minus. Okay, I will also skip this. And the final area with structure changes is located here. In this manganese calcium cluster, you can see there are a lot of different signals, means that there are larger structure changes occurring in this cluster. For example, this pair of negative positive electron density suggests that this atom has moved from in this direction, and this is one of the manganese ion, manganese 4, and there's a pair of negative positive electron density. This is suggests movement of this amino acid residue, which is glutamate 189, and also here, and here, and here. And the two most important structure changes we saw is one is here and one is here. And this is positive electron density without corresponding negative electron density, because this negative electron density makes pairs with this positive and this positive. So this positive electron density does not have a corresponding negative electron density. So we can model a new water molecule or oxygen atom into this positive electron density, and this is called O6. And this position is very close to the O5 atom. So in the S3 state, there is a new water molecule comes in to a close position to O5, and these two oxygen atoms may be able to form a O bond to produce a molecular oxygen. And the whole structure becomes in the S3 state compared with the S1 state. You can see the S1 state O5 is located here, and the S3 state, the new water molecule, or oxygen comes into this position, and they are able to make an O bond. And this bond was broken in the S3 state. So when you give another light illumination, this bond between oxygen and manganese O5 may be cut out to produce one molecule oxygen, and a new water molecule may come in to replace O5 to return the structure into the original state. This is the final possible mechanism for O bond formation and the site for the reaction to occur. And in order for this O6 oxygen atom to come in, this is a short amino acid residue has to change its position. The side chain was shifted in this direction by 0.5 angstrom. And if this amino acid residue does not change its structure, its original position is here, then it will have this distance to O6 of 2.3 angstrom, and this distance is too short for the O6 oxygen come into this position. So this amino acid residue has to move in this direction by 0.5 angstrom. And the second largest and important structure changes is here. Water molecule originally is located here, but there is a negative electron density suggests that this water molecule has disappeared after two flash illumination. And this water molecule forms an extended hydrogen bonding network through this manganese calcium cluster O4 and another water molecule, and this water molecule, then to the surface of the protein complex. And this water molecule, we suggest that this hydrogen bonding network is required for the protons to be transferred through this hydrogen bonding network through here to the outside of the protein complex. And because the proton is removed, transferred through this hydrogen bonding network, this water molecule is disordered temporarily in order to break the hydrogen bonding network here to prevent the proton come back again through this hydrogen bonding network. So this is also a very important reaction to transfer the proton and prevent the proton to come back again through this hydrogen bonding network. Okay, this is the structure and the function of the water splitting and PS2. And in the final several minutes, I would like to introduce several of our recent work based on, in terms of the evolution, PS2 is one type of photosystem. I said there are two photosystems, PS1 and PS2. And PS2 is called a type 2 reaction center. It consists of D1, D2 subunits, and it is considered to be originated from non-photosynthetic bacterial reaction center, which is called LM subunits reaction center. And the structure of this photosynthetic LM subunits has been solved many years ago, but in the cells, this reaction center are surrounded by a number of light harvesting protein complex called light harvesting 1, and forming a circle to encircle the reaction center, RC in the middle. And this is also a super complex, which consists of 16 pairs of electron subunits, alpha beta subunits. That means that there are 32 protein subunits of light harvesting 1 complex, and in the middle there are 4 subunits of reaction center. So this complex consists of 36 protein subunits with a molecular weight of 400 kilodalton. And one of my colleagues just solved this structure at 1.9 Angstrom resolution, and he just published this paper in this year. And we can see the arrangements of bacteriochlorophylls here, and a number of water molecules, and bacterial beta-carotenes, and a number of cofactors. And interestingly, there are several ubiquinol molecules, and one is QB, but the second one is very close to QB, which means that this QB is just waiting for this ubiquinol is waiting for the QB to be double protonated and removed. After it is released from this binding site, this ubiquinol will come in to replace the bound ubiquinol QB. The second one is located in here, and there is a hole between the light harvesting alpha and beta subunits for the ubiquinol to be able to transport. So this hole to the outside of the ring. The ring is completely closed, so we need some hole. You need some holes for the transport of the quinol molecules inside into the inside and outside of the ring structure. And in terms of the evolution, the non-photosynthetic bacteria is evolved to PS2 in cyanobacteria, oxygenic cyanobacteria. Then from cyanobacteria, it is evolved to lead alga, on one side the lead alga and the diatoms, and on the other hand, it's green alga and hyaplants. So we are also interested in the structure of PS2 in these different species of organisms, because there are several different subunits in the PS2 complex, core complex, from cyanobacteria to lead alga and diatoms and to hyaplants. You see, most of them are the same, but some of them are not present in cyanobacteria, or yes. So also, most importantly, that the light harvesting complex are very much different. from cyanobacteria to red alga and to diatoms and to higher plants. So we solved the structure of red alga PS2 and also diatom recently. And from the red alga, there is a fourth hydrophilic extreme subunit. It is called PSVQ, which is not present in cyanobacterial PS2. And also there are two extra transmembranous helices. We assign a chain W and a chain S in red alga, which are not found in cyanobacterial PS2. And this is the structure of diatom, from diatom PS2. And in complex with the light harvesting complex from diatom, which is called FCP. This means that it's fucoxanthin, chlorophyll C binding protein. And in the middle, you see there's a PS2 dimer, core dimer, which is similar to the PS2 dimer from cyanobacteria, but it is surrounded by a large number of FCP, light harvesting proteins here. And one form of the FCP forms a tetramer here. And there are several monomers also connecting the tetramer with the PS2 core. And looking from this side, you can see there are 5 extreme subunits involved in the water splitting reaction. And 2 of them, PSBQ minus, PSBQ prime, and PSB31 are not found in the cyanobacterial PS2. But this is the structure is solved by a cloud electron microscope and at a resolution of around 3.5 angstrom. So the resolution is not so high, and the arrangement of pigments may not be so, the detailed arrangement may not be clear. So one of my colleagues also solved, made the crystal of one FCP subunit and solved its structure at a resolution of 1.8 angstrom by X-ray crystallography. And this is the whole structure of one single FCP subunit. It is interesting because it binds chlorophyll C, and this red one are 2 chlorophyll Cs, and also binds a number of fucoxanthin carotenoids, which is very unique, different from higher plant and cyanobacterial PS2. And based on the structure, we can deduce the energy transfer within this FCP complex. And these distances suggests which chlorophyll will transfer energy to which chlorophyll. I will not go into detail of these structures. And the last one is, I just mentioned, talked on the PS2. And we also solved the structure of photosystem 1. And in terms of evolution, photosystem 1 also has changed its composition from cyanobacteria to higher plants. We first solved the structure of PS2 in complex with light harvesting 1 complex from a higher plant, P. And this is the core structure of PS1, and these 4 subunits are light harvesting 1 subunits surrounding in one side of the PS1 complex. And they harvest energy and transfer the energy to the reaction center here of PS1. And if we remove these protein backbones and just look at the arrangement of pigments, there are a lot of chlorophylls and carotenoids in the reaction center, RC, and also in the LHC1 subunits. And based on their distances and orientations arrangement, we can deduce how the light energy is transferred from the light harvesting subunits to the reaction center. And these are 2 important major energy transfer pathways from the light harvesting subunits to the reaction center. And then in the middle, there are small low efficiency energy transfer pathways from the light harvesting complex to the reaction center. Okay, this is the structure of PS1, and we also saw the structure of PS1 and lattice 1 complex from the lead by electron microscope. And the interesting one from the lead is that the lead contains two types of PS1 LHC1 structure. This is called LHCr because it's from the lead. One type of the structure contains three LHC1 subunits, LHCr subunits. The lead contains only three genes of the LHC lattice subunits, so it contains three subunits, lattice subunits, in one side associated in this side. And this side is similar to the higher plant PS1 LH1 subunits. But the second type of the lead PS1 has two additional LH1 subunits bind to the opposite side of the major LH1 subunits. So it contains in total 5 LH1 subunits, and we think that this type of structure is required for the lead to survive in low light intensity, because in the low light intensity you need more light harvesting subunits to harvest energy. And based on the this is the comparison between the lead and higher plant structure, and based on the arrangement of these chlorophylls, we can deduce energy transfer pathways also in the lead PS1 LH1 subunits. There are three connection sites here, and these are the same in the two types of the structure, but this side, it exists only in one type of the structure, which has 5 LH1 subunits. And we just published this paper in this year. Okay, I think I finished this and all I would like to introduce, and finally I would like to introduce my co-workers. The worker on photosystem 2 and free electron laser done in collaboration with Professor Soiwata in Kyoto University in Japan, and several people from University of Tokyo and Osaka University. And these are the members from my group here. And also the work on PS1 is done in collaboration with a group from Institute of Botany of Chinese Academy of Science, Professor Kwang's group. And this is Professor Kwang in Beijing. Okay, finally, I would like to thank you for your attention.
But usually, I guess the big one is that the creation of the winning day. What is the difference of
okay, to say the true Big Bang is not the universe of Big Bang, but this is they call it biological Big Bang evolution, because the species of organism increased very much during that time.
One of them, I read all these stuff of papers, difficult to find information about oxygen evolution, deep oxygen evolution, all complexes which we use it for volcanoes, elongatus, or the oxygen evolution, yield of oxygen evolution.
Yield of oxygen evolution.
The core complexes which you use.
When we measure the oxygen evolving activity, it's usually 3,000 micromoles per second per,
As I understand, the problem is still exists with situation about substrate weight about waters. So you show different positions.
the substrate of oxygen or water, the substrate.
Substrate.
Yeah, we think that one is 05, the second one is 06. But we don't know, actually we do not know where the 06 comes from. And there's probably some experimental errors in the distance between 05 and 06. But we are sure that there is a new water molecule come in the S3 state. And excuse me. It's not bicarbonate. I'm sorry.
If you have any option, you specially investigated the water channels, like in Barber.
Yeah, I did not mention the channels. There are several channels and hydrogen bonding networks based on the structure. And these, we cannot still say which channel is for what. We are sure that there's water channels, and there are proton channels, and several of the hydrogen bonding network, we think that are involved in proton transfer. But water channel is, no, we don't know.
And next question is about tyrosine D, the net hydrogen atom network around tyrosine D. So is function is of this network is similar that about around with tyrosine YZ?
Yes, it's similar. There's also history.
So can easily transfer protons from.
Well, when if there's the YZ functions in the normal case, YD will not function. But in our crystal, accidentally we saw the structure changes around YD. And we think that a very small part of the reaction center, there's YD remains reduced. So, remains, yeah. So when we illuminate with one flash even, there is a proton transfer around YD. Normally it will not occur if YZ is fully functional.
It is functional when YZ function somehow inhibited.
Yeah, very small part of the core.
So, one more question, optional question. I want to ask the function of these small proteins you can see in the structure.
Yes, yes.
Do you have any idea of
Yeah, some of the small proteins is required to stabilize their interaction partner. If you remove the small proteins, then you will create a space, and then the structure that originally is interacting with the small proteins will become changed.
Means only structural function.
Yeah, only structure, the stability for the whole complex.
Thank you very much.
What small protein is very important for strangulation?
Well, the reaction center is D1, D2, and the small proteins which are very closer to D1, D2 is very important. And G is one of the important. If small proteins, if we remove G, it almost die. It appears to be almost die. And the cytochrome B559, EF subunits are also important. If we remove them, the PS2 will not work, it will die. And others, some small proteins in the edge of the complex, some of them are actually not important. So when we remove them, we can only see very little effects, or only even almost no significant effects.
Çox sağ olun maraqlı çıxış üçün. Çox sağ olun maraqlı çıxış üçün. Sağ olun maraqlı çıxış üçün. Mən iki sualım var. Birinci sual ondan ibarətdir ki, o stul siz göstərdiniz, model. Stul, oksigenin ayrılması, suyun parçalanması, oksigenin ayrılması modeli. Orada o, həmin o stulda, modelde daha doğrusu, kalsiyum və mangan atomlarını başka iki valentli metallarla əvəz eləmək olar mı? Onda onun o parçalanma funksiyası necə olacaq? Və ikinci sual ondan ibarətdir ki, siz orada göstərdiniz qırmızı yosunlar, sonra canabakteriyalar və ən nihayət ali bitkilərdə fotosistem 2'nin tərkibindən daxil olan komponentlər, jurnal komponentləri. Və oradan aydın oldu ki, sizin slaytdan onların həmin o su vahidlər demək olar ki, eynidir. Bu belədir, yoxsa onlar o su vahidlərə görə, tərkibinə görə yosunlarda və ali bitkilərdə bir qədər fərqlidir.
Yes, the first question, the manganese cannot be replaced by any other divalent cations. Only the calcium can be replaced by strontium. But if we replace calcium with strontium, the activity will be decreased by 30 to 40%. Okay.
Thank you.
The second question is that the core part, the most important part of PS2, remain the same from cyanobacteria to higher plants. But there are some of the small subunits and also some of the hydrophilic extrinsic subunits involved in water splitting are different between species. So we solved several types of the structure from different organisms, and we saw some of the subunits are not present in cyanobacteria, and some in cyanobacteria are replaced by different subunits in diatoms. So we are also interested in the overall structure and the subunit changes during evolution. But I have to say that the most important core of PS2 remain the same, and in particular, the water splitting structure is completely the same. So there is only one type of catalyst for water splitting in the nature, and this is because water splitting is very difficult reaction, and nature can only develop one structure. There is no other structure that can split water.
Bir dənə sual. Bir dənə də sual bir dənə çıxır. Siz dediniz ki, kalsiyumu platinlə əvəz edəndə aktivlik azalır. Bunu neylə izah etmək olar? Kalsiyumun kalsiyum atomunun orada hansı xassəsi ilə izah eləmək olar bunu? İyonundur.
We solved the structure with strontium replacing calcium, and we saw very small changes in the distances between strontium and oxygen and strontium and water molecule. So the distances I introduced today in the native structure is the best one for this catalyst to be able to split water. So if you change very slightly the distances, atomic distances, it will change the activity and the efficiency will be lowered. So this is actually very optimized structure, and you cannot change it anymore. Even a very small distance change will lower your efficiency or even destroy the activity completely.
Hi.
I want to ask, is it possible to repair molecules damaged by
Microphone.
I want to ask, is it possible to repair molecules damaged by X-ray radiation?
Is it possible to repair?
Repair, yes.
Repair? No, it's not possible because we are working with the isolated proteins, and once you destroy, you damage the structure, the protein. It's not possible to repair it.
Okay, and you revealed us two types of photosynthesis, yes? And is it possible? Can a new type of photosynthesis appear in process of evolution?
Excuse me. Two types of yeah. Yeah.
Yes, two types. Two types.
Okay, two types of reaction center,
Yes.
and there are two types of photosynthetic bacteria. One contains type 2 reaction center, which is a purple bacteria. The other one type is containing type 1 reaction center, which is a green bacteria. So these are developed as considered to be the ancestor of PS2 and PS1 respectively. So the type 1 bacteria is the ancestor of PS1, and the type 2 is the ancestor of PS2. And in the oxygenic cyanobacteria, these two types of bacteria combine together to produce the now oxygenic photosystems containing both PS2 and PS1. But in the bacteria, they are living separately.
Thank you.
I'd like to extend my sincere thanks to you again, and I hope to see you meet in Baku again. Thank you.